Hello, everyone. Uh, we started a new topic last week that was floating point numbers and their representation. That topic is of A2 level, A level topic. So let us first revise what we did last time and then we proceed further. Okay. We started off floating point and the point that required to be considered first was that to, uh, to go for floating point, we should understand fixed point numbers first. Fixed point numbers, as I said, that were, hold on. In actual form, fixed point numbers were actually being used with binary coded decimal. Over here, we have taken it for the representation. In fixed point, we need to consider, like in denary numbers, we consider 10 to power 0, 10 to power 1, 10 to power 2, 10 to power 3, and then 10 to power minus 1 and minus 2 and minus 3. But over here in base 2 system, we use binary or 2 number or base 2. 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, and this goes towards the left, and 2 to power minus 1, 2 to power minus 2, 2 to power minus 3, and 2 to power minus 4 towards the right. And if we simplify these, this would become 1, 2, 4, 8, 16, 32, 64, 128. And over here on the right side, it is 0 0.5, 0.25, 0.125, 0.0625, and 0.03125. Never to forget that these are fixed point numbers where the point is fixed and the whole number increasing on the right side and fractional number is increasing on the right side. And whole number when goes towards the left, it is increasing by 2, and when it goes on the right side of the point, it is decreasing by 2. I mean, it is getting half at every stage. For students, it is important to remember that uh, these digits, since we would not have any calculator in exam, we need to remember these fractions 0.5, 0.25, 0.125, 0.0625, and 0.03125. In exam, until now, we did not have any question which is requiring us to go any further than 0.03125. So first, whatever the number that is required to be converted to its floating point form needs to be converted to fixed point, and from fixed point then we go to floating point. Let's say we have got this number 19.1875. We can achieve 19 by having 1 under 16 and 2. So this would become 10011. And 1875, if we add 0.125 and 0.0625, it would become 1875. So the whole number becomes 10011.0011. So this is the binary fixed point representation of 19.1875. Now this, in order to convert it from fixed point to floating point, we will then take this point all the way towards the left. Now, before we go any further, I discussed this phenomenon of floating point number, which I called floating point chemistry. Total number of bits available for floating point is called the word size. And out of this word size, few bits are allocated for exponent and few bits are allocated for mantissa. In the generalized form, floating point is standardized form in the binary. So this right side is exponent And this is showing that how many times the point has moved and has to move back to have the actual number back. And this mantissa is about the significant. In here, computer science, we call it mantissa. So if it is 2 into power 10 to power 3, that 10 to power 3 is exponent and 2 is significant or mantissa over here. But it is a restriction that point has to lie between first two bits. So wherever the point is, we have to move it all the way so that we could save it in between first two bits, because we don't have any representation in exponent, sorry, in floating point to show this radix or point. So what we do, we fix it in between first two bits, and whenever we see a number, we understand that the point is lying between the two. So what exactly happens, that this is the formation of floating point, out of which it is divided into two parts. First one is exponent, the other one is mantissa. Remember, you might get exponent on the left side. It really does not matter because these are two different numbers. They may be on the left right or right left. That doesn't matter. It doesn't mean anything. Mantissa is in fraction because it has got a point lying between first two bits, and it is always fixed. All right, so now since mantissa has got a point in it, it is in fraction form, and exponent is telling how many times the point has to move back towards the right or the left in order to get the original number. It is always an integer. Now, they both are in 2's complement. 2's complement means whatever this most significant bit, it has to be in the negative form. So if it is exponent, then we have got 1, 2, 3, 4, 5 bits over here. So 1, 2, 4, 8, 16. 16 is the most significant bits worth. So it will be negative. Over here, since it is a point, so in mantissa minus this 1 is always negative, because mantissa increase towards the right side. If it is increasing, it means that it has increasing fractional number. Since exponent is increasing towards the left side, it means that it is increasing by 2. Now, when we fill the mantissa, we fill it from left to right. So if we have got the situation when we have got more to fill and less space in mantissa bits, then we fill it as much as we can and drop the rest of the bits. That is said to be uh, overflow. And if it is in exponent, that case we fill it from right to left and we drop it from the left, it is overflow. Sometimes we have got other way around situation, then when we have got less number to fill and more space, in that case we fill rest of the bits with 0, either in mantissa or exponent, and it's said to be underflow. Remember, fractions cannot be dealt by the ordinary arithmetic and logic unit of a CPU, because arithmetic unit in ALU only deals with mm, integer numbers. So computers have got an extra unit inside their processor, which is said to be floating point unit, that deals with the numbers in fractions. So now we have got fixed point representation in binary of 19.1875. What basically happens, that once we get the fixed point, we have got a point in here, but since we cannot keep the point anywhere, we have to move it. So the rule says that move it to the extreme left, all the way towards the left, all the way towards the left. When we move it all the way towards the left, that would become 0.100110011, that is over here. And mind it that you need to put a 0 on the left so that it should become 0.100110011. Without that a 0, it would matter, because that 0 fits in here, and the 0 in this bit is said to be a positive floating point number, and 1 in here shows that it is a negative. So in this case, since this is a positive number, when we move the point towards the left, extreme towards the left, it is actually a positive number, and we have to put 0 there. All right, now once we have got this, we introduce the exponent part, and since this number system is binary, So our base is 2. So this number multiplied by 2 to the power 5. Why 5? Because we moved 1, 2, 3, 4, 5 points. So in order to get this number back, we have to move the point right as many times as exponent. If the exponent is positive, it means that this point will move right. And if the exponent is negative, it means that this point will move towards the left. So now afterward, this is the situation: 0.100111111 into 2 to power 5, where this point, this multiply, and this base 2 has no space in this word size. So what we do, we remove them. Since these are decided, they don't go anywhere in floating point. The point always lies between first two bits. This multiply is a fact, and this base 2 is a fact. We don't save it. So what we do, we just remove them and convert this 5 into its binary form. So what we do, we write it this way: 0 1 0 0 1 1 1 and 5 1 2 4 and 8. Now you need to understand that you have to put this 0. If you don't put this 0, this would become 1 2 minus 4, and the number will become minus 3 instead of 5. So you have to put 0 over here. Now once you convert it to this form, then we will look into that how many bits are available for mantissa and how many bits are available for exponent. So let's say 10 bits are available for mantissa. We start filling these from left to right. So we will fill it 0 1 0 0 1 1 0 1 1. These are 1 2 3 4 5 6 7 8 9 10. And then since 10 bits were available and these are 10 bits, so it got filled in over here. If you fill it, we will fill it from right to left. So 1 2 3 4, and then we have got two more bits. This is underflow, so we will fill two zeros. Afterwards, I asked you to solve this question. If you would solve this question, you would see that in 10 bits mantissa, we get to drop this 0625. And once we save it, the 11th bit that would be saving 0625 will be dropped off. So the number that was given was plus 36.5625. But ultimately, the number that will be saved will only be 36.5. Afterwards, we discussed this was from denary to binary form in floating point, and this is from binary to denary floating point. So I saved the answer from this question 36.5625, but 0625 is dropped, so we just took the original one. uh, since this is a positive number, we have got 0 over here. So this number is 0 1 0 0 1 0 0 1 0 0, and the power is 124, which is 6. Now first we need to convert it to the standard form, and in standard form we know that the point lies between first two bit. Here we go, and this is the exponent. So this would be 10, sorry, multiply 2 to power 6. And we don't need to put these trailing zeros in mantissa and leading zeros in exponent. So this has become 0.1001001 into 2 to power 6. Then we resolve this exponent by having this point move towards right. Why right? Because the exponent is positive, and how many times? 6 times. So 1 2 3 4 5 6. This has become 1001000.1, and if we solve it, this would become 1 2 4 8 16 and 32. So 32 plus 4, this has become plus 36, and 0.1 has become 0.5. So this is your answer. Afterwards, we discussed that um we until now have resolved positive denary to floating point binary and positive floating point binary to denary. Now let's solve it negative denary floating point to binaries. Let's say we have got a number given minus 20.75, and we have to fit it in 8 bits mantissa and 4 bits exponent. For that, first thing that you have to do, as per the rule, we will ignore this negative sign and we solve it 20.75 as a positive number. So ignore this negative sign, we solve it. 1, 2, 4, 8, 16. 16 plus 4, 20. 0.75 means zero point 0.5 and 0.25. This is the fixed point representation of 20.75 in binary form. Then we move the point all the way towards the left. This would become 0.1010011. And how many times the point has moved? 1, 2, 3, 4, 5. So this would become into 2 to power 5. Once that is done, we will remove this point, multiply, and 2. We will be saving only 0, 1, 0, 1, 0, 0, 1. Uh, and with a space to distinct this mantissa from exponent, we will put 0, 1, 0, 1 as the binary of integer binary of 5. Then we have to put it in 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. This one got dropped over here because we don't have any spaces in actual number. 0, 1, 2, 3, 4, 5, 6, 7, 8. So have I made any mistake here? 1, 2, 3, 4, 5, 6, 7, 8. No, the number is actual. Now, afterwards, we know that this is a positive 20.75. We have to convert it to negative form. For that, what we do, we keep the exponent same. Remember, we keep the exponent same. And from the right side to the first one in mantissa, from the right side to the first one in mantissa, we keep digits same and toggle the rest, convert the rest to their opposite. Means we'll make 1001. So remember, if the number is negative, we take it as a positive number. We start solving it. Once we get down to the answer, what we do, we keep the exponent same. And in mantissa, from the right side to the first one, we keep every bit same and toggle the rest, convert the rest, flip the rest. All right. Then we discussed that these floating point numbers are non-reliable since they tend to lose perfection or precision in mantissa. We cannot keep them for monetary values in accounts and banking and any other situation where we have to keep the precision to its 100th percentile. So where do we use it? We use it at rest of the places, in stats, in graphics, in uh, gaming, and anywhere where we can afford to round off numbers. If we cannot afford to round off numbers, we don't use floating point over there. So having floating point representation or data type in languages for any numbers which are saving any currency or any type of situation where we need to keep the precision is not good. For that, we should choose any form of the BCD. Like in Visual Basic, we have got decimal number format, which is actually made up of BCD. Now, after that, we discuss negative floating point numbers. How do we convert them? So, first of all, I told you that if we look at a number in binary floating point and the number starts in mantissa with 0, then it is a positive number. If the number starts with 1, then it is negative. So if it is a negative, first we have to convert it from negative to the positive form so that we could solve it. Similarly, as we did over here, if it is negative, we first made it positive to solve it. So what we do, we keep the exponent same, and in the mantissa from the right side to the first one, we keep the whole thing same and toggle the rest. Once we do that, the number is flipped from negative to the positive form. Afterwards, we go to the standardized form. This would be by putting 0.0 over here, ignoring all the zeros in the trailing side of mantissa, and over here on the leading side of exponent, this would become 0.10101 into 2 to power 4124. And afterwards, we see that this is positive exponent. So we move the point 4 times towards the right, 1010.1. So this has become this. So 1, 2, 4, 8, 8 and 2 become 10 and 0.5. So the original number is 10.5. And since the original number was negative, we put a negative sign over there. So this has become minus 10.5. So until this point we discussed and I gave you these questions. Let's move forward. So let's talk about normalization. Normalization is an important concept without which computer does not save any number in computer's memory. So it is actually very important to normalize any floating point number before you find the answer. Remember that whatever the numbers that we have discussed until now, they all were normalized. Now, what is normalization? First of all, I told you that whatever the floating point number that is saved is actually saved in given number of bits. That given number of bits is called word size. So word size is fixed. In word size, what we do, we actually divide the word size into two parts. First is mantissa, the other one is exponent. As of now, we know that if we have got a number in exponent, that means that how many times we are moving the point. So if we move the point to the farthest side, farthest on the right side, that means that we are increasing the range. If we are moving the point to the farthest side towards the left, it means that we are decreasing the range or the size of the number. And similarly, we discussed and we saw that in mantissa, if the bit is dropped, the fraction is dropped. So if you do remember in first slide, we had a number plus 36.5625, and when we saved it in 10 bits mantissa and 6-bit exponent, we lost 0.0625. Why? Because we had no space in mantissa to save that point. That was the 11th bit. So it means that in mantissa, whenever there is a point dropped, it means it would be a smaller fraction, but that will disturb the whole number. That smaller drop might be leading to a rounding of the number, but rounding of the number sometimes matters, sometimes does not. If it matters, then we cannot use the floating point. So we can say that in the word size for floating point, size of the mantissa and exponent should have a trade-off where we don't lose anything. So let's say this is a slider between mantissa and exponent, and the size of the word is fixed. We cannot afford to change the size of the word. So let's say if it is a slider and we move it towards the left, we decrease the accuracy, but we increase the range. And similarly, if we move this slider towards the right, we increase the accuracy, but we decrease the range. So we can say that mantissa is inversely proportional to exponent. This is a common question that appears in exam. What is the relationship between mantissa and exponent? So the relationship between mantissa and exponent is they're inversely proportional to each other. If we increase mantissa, we increase accuracy, but we decrease range because this number of bits allocated in exponent is decreased. Similarly, if we increase the size of exponent, it is a trade-off. Now, this normalization concerns mantissa and, in other words, accuracy. Normalization is an attempt to have more bits in mantissa in case if it is possible, not by force, in case if it is possible. How do we know it? Let's learn about it. Let's first see what is normalization. So computer cannot save non-normalized floating point number. So mind it, if a number is non-normalized, we cannot afford to save it. Computer does not save it. That is by rule. Normalization is an attempt to make floating point more accurate by having more space in mantissa and reducing a chance of bit dropped in mantissa from the right side. We discussed it already. Then due to normalization issue, computer cannot save a 0 as floating point value. We will shed few thoughts on it afterwards, but not now. 0 requires, we will discuss about it. Computers uses the smallest positive number. We will discuss about these two. So let's start. How do we know if the number is normalized or non-normalized? This is very simple. If the first two bits are same, means they both are zeros or they both are ones, it means that number is non-normalized. Until now, whatever the number that we have dealt with, they all had first two bits different. If it is different, then it is fine, computer will save it. If these are not different, if they are same, it means that number is normalized, computer would not save it. So this number is said to be non-normalized as first two bits are the same. Computer will not save this floating point number. So what we do in order to make it normalized, how do we do that? So this is the same number 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, and 0, 1, 1, 0. So this is a number. So what do we do? How do we know? We now know that if first two bits are same, then we have to do something because these are non-normalized number and we have to make it normalized. So what we do at first we mark. Achha, this marking is all is in your mind. This is not in actual terms. Marking is how we look at this number and we have to mark that from the first number on the right side of it in Mantissa, we have to mark that which two numbers are different. So from this, we mark until the first one. So if it is 1, then to the first 0. If it is 0, then to the first 1. So in between two marked numbers, whatever the bits, they must be same as the first bit. So if we mark from 0 to 1, all the zeros in the middle, they are making this number non-normalized. So what we have to do, we have to remove them. These will be taken out. Rest will be shifted to the left. So these bits will be shifted to the left. So first we take it out, These bits will be shifted to the right, to the left, and on the right, 3 new spaces will be created because of the shifting, because the word size is same. So in those 3 spaces, we may have the bits which are being dropped get back into the mantissa. So get the idea? So why do we normalize? Because if it is possible, we remove few bits from the start so that if any of the bits are dropping, they can get back in. But for now, what we do, we shift them towards the left, and whatever the 3 spaces that are created, we will be putting zeros in it. But there would be a trade-off. Trade-off will be on the exponent. So now let's see, we removed these first 3 bits, second, third, and fourth bits, which are making it non-normalized. We are shifting rest of the bits towards the left. And this is the number now, 0, 1, 0, 1, 0, 1, 0. All right. Now, there is an effect of it on the exponent. Now, what is happening? These 3 bits are removed. We will subtract the number of digits which are being removed, which is 3. 1, 2, 3. What is our exponent? 1, 2, 4, 6. So these number of digits removed will be subtracted from 6. So this will become 3. So now the original number was 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0. This has become 0, 1, 0, 1, 0, 1, 0. And these 3 bits were fitted in. And then afterwards, we subtracted the number of digits removed in mantissa from the value of exponent, and that is now 3. So this is normalized number and this is non-normalized number. So we can see over here that these 2 bits are different. So this is normalized and these 2 bits are same. This is non-normalized. Now the question is raised, the number has been changed. Yes, it has been changed, but the value of these 2 numbers are the same. So there are occasions in past paper questions when we had such questions that they asked us to prove that if these 2 numbers are the same. So we have to solve it. Now see over here, I have solved it. So this is 6 times. So I moved the point 6 times. So this has become 101.01. That is 5.25 positive. Over here, this is 3 times. So I moved it 3 times. Even moving it 3 times after normalization, this makes it 101.01, which is the same, 5.25. So if the number is non-normalized or normalized, the values are same. So computer saves which one? The one that is normalized over here. This will never be saved. So mind it. Now, if it is a negative number, I told you that how do we find it if the number is normalized? By having a watch on first two bits. If first two bits are same, it means that it is non-normalized, and if they are different, then it is normalized. So I told you earlier that if we see a negative floating point number or negative denary number that needs to be converted, first we remove the negative sign on it. But now I'm telling you that if the number is non-normalized, first try to normalize it. Afterwards, we will make it a positive number. So we marked first one and the different bit zero so that we could see that how many bits needs to be dropped. So this is 1110. So we marked the first one and the zero, and in between there are two bits which are actually redundant, and we need to remove them in order to make this number normalize. So we will remove it. This would become 101010, and then we will put two zeros over here because these 1 2 3 4 5 bits will be shifted towards the left, and the effect would be that this is 1 2 4. This is 4. 2 will be subtracted from it, and this would become 2. Now we can see, so this has become 101010, and these two zeros are fit in because these bits are moved towards the left to find these two spaces blank, and we will put 0 in it, and this 4 has become 2 because we have subtracted number of bits removed from the exponent. Now let's convert it to the form that we know of. So first we will keep the exponent same, and to the first one in the mantissa will keep it same and toggle the rest, and then we solved it usually. So first we normalized it, we solved it as a positive number then, and then we have found that it is 2.75, and we will put minus sign over here since the original number was negative. So this is negative 2.75. Now try solving these three questions. You have got, let's say, 5 minutes. Meanwhile, I'm available on chat. If you have any question, ask me the question. All right. I hope that you would have already done it. There are questions in past paper where what happens that sometimes from the start we don't have the number in non-normalized form. Rather, we start with the number that is normalized, but during the way, what happens that at some stage, at some point, the number becomes non-normalized. So minded that it is not always the case that the non-normalized number will be given right from the start. Rather, sometimes it becomes non-normalized during the execution. All right. So now let's see. We have got this number. This is 0 0.5. We have to fill it in 5 bits mantissa and 3 bits exponent. Let's say the word size is 8. Obviously, we will be solving it like 0 0.5 first, as we don't consider negative sign, and then how we will put it 0.1. So this is the fixed point representation of 0 0.5 in binary form, 0.1. Now we have to fit it in 5 bits mantissa. So this will be fitted in 0, 1, 0, 0, 0, 0, and exponent will be all zeros because we don't have to move point anywhere. This is 0.5, this will remain 0.5. So we don't have exponent either positive or negative because we have to make it 0.5. So this is 0.5, and we don't have to move the point anywhere because the point lies where it lies in order to have it for 0.5. So we have this exponent over here. Now let's fill it. 5 bits mantissa, 0, 1, 0, 0, and 0, 0, 0. So now this number was originally negative. So how do we convert it to the from positive to negative form? By having this mantissa same, and to the first one we will keep the mantissa, sorry, having exponent same, and to the first one we will keep the mantissa same and toggle the rest. So now when we will do it, to the first one we will keep it same and toggle the rest. This becomes non-normalized. So you checked it that when the number was given and we converted to its form, fixed form, and then when we convert it to the floating point, it has no problem. But once we convert it to the negative form so that we could actually have a negative 0 0.5, we see that this is now non-normalized. So we have to now normalize it. So once we normalize it, how do? We mark first 2 bits which are different, and we see that this one is now redundant. We take this number out, and since this is 0, 0 minus 1 becomes minus 1. So this will become 1, 0, 0, 0, 0, and for minus 1 we know that all ones will be placed. This one will be removed. So 1, 2 minus 4, this becomes minus 1. So mind it, sometimes you may have such questions where the number originally is not non-normalized, but during some situation, during the course of solution, at some stage, a situation arises where the number becomes non-normalized. All right. Now let's go further. Range. This is also another aspect of floating point numbers where we are given a word size and the bifurcation between the mantissa and exponent, and we have to find what is the largest positive number that we can save, what is the smallest positive number that we can save, what is the largest negative number. Largest negative number means that is smallest uh, magnitude negative number, and smallest negative number means largest magnitude negative number. Sometimes mind it, this shows up in exam that smallest magnitude negative number is actually the largest negative number, and largest magnitude negative number means smallest negative. All right. Now, we discussed over here that due to the normalization issue, computer cannot save 0 as floating point value. 0 requires both mantis and exponents to be all zeros. So it is obvious that if we like to save zeros, we have to have mantissa all zeros and exponent all zeros. So it is not possible to normalize a 0 because 0 has got all zeros. For normalization, we have to have at least one bit positive, means one bit 1, at least one bit 1, so that we could normalize it. If we don't have one in it, we cannot normalize it because we cannot then mark as we marked over here, as we marked over here. If we suppose that if we have all zeros, how we will mark that which two bits are different? We won't be able to do so. So if we won't be able to do so, it means that we cannot save 0. 0 cannot be saved. So how do we save 0? Computer uses smallest positive number as the representation of 0 digit. So it is another reason we cannot use floating point for monetary values, because sometimes if someone's account is actually empty, someone has taken all the money out of their account in a bank, how do we solve it? By having some amount in it. That's not possible. So we use smallest positive number. So this 0, I have tried to have this integer in both positive and negative form over here with the 0 in here, but this 0 is fictitious, does not exist. This is just to differentiate between the positive side and the negative side. So this is fictitious, doesn't exist in binary. So this is +1, +2, +4, +8, +16 goes towards the right. So this is said to be the positive, smallest positive number, which is the positive number that is close to 0. And then we have got the largest positive number, which is farthest from 0. So on the negative side, it is, as we know that the smallest the negative number, larger it is. And the bigger the negative number, the smallest it is. So the negative number that is close to 0 is actually the largest negative number. And we know that in mantissa, it is always less than 1. So if it is less than 1, it means that it is further close to 0. And if it is a greater magnitude number, then it means that it is the smallest negative. So the smallest negative number is the number farthest from the 0 on the negative side. And the largest negative number is actually the number which is closest to the 0. And we also call it smallest magnitude negative number, which is largest negative, and bigger magnitude negative number that is said to be smallest negative number. Now, now this chart is actually required to be remembered thoroughly. First thing is, how do we come up with this chart? I need you to memorize this chart. This chart needs to be memorized. All right, so what actually happens that, let's draw this chart one by one so that we have an idea that how do we do it. First of all, largest positive number. So we have to have largest mantissa in it. So let's say that we are doing it with 4 bits in mantissa and 4 bits in exponent. All right. So these 4 bits in Mantissa are 1, 2, 4, 8. So as we know that Mantissa is in 2's complement. So this is the largest positive number that we can accommodate in it. 1, 2, 4, 4, 5, 6, and 7. And then it comes to exponent. I'm sorry, I was talking about exponent. So the 7 is the highest positive number that we can save in exponent. In Mantissa, the leftmost bit is -1, that is actually positive. So this is 0.5, 0.25, 125. These are the Mantissa's positive values. So this is the largest positive number that we can accommodate in Mantissa, and this is the largest positive number we can accommodate in exponent. And if we solve it, then we have got the largest positive number which is possible in 4 bits Mantissa and 4 bits exponent. So Mantissa is largest positive and exponent is largest positive. So smallest positive, we have smallest positive Mantissa and smallest negative exponent. Remember, smallest negative is the highest magnitude negative number. So now smallest positive is 0, 1, 0, 0. I know that few of you will cross argue that smallest positive would be the positive where we have got 1 on this side. But the thing is, we cannot have 1 on this side because that will make it 0, 0, 0, 1. And if we have got 0, 0, 0, 1, that is non-normalized, computer will not be able to save that smallest positive number. So I call it roughly normalized. So we remove this 1 and rather we put 1 over here. So instead of 0.125 as the smallest positive number that can be accommodated in 4 bits Mantissa, we are making it 0.5. I know there are several justifications about it, but to me, this is another reason we cannot use floating point numbers as the currency or any monetary values that we want to save. So mind it, you have to remember this, that instead of 0.125, we will be saving 0.5 as the smallest positive number, and the smallest negative number would be, obviously we know that this is 1, -1. So -1 is the smallest negative number that is possible in 4 bits exponent. Now, remember, this is roughly normalized. Same with the largest negative number. Largest negative number should be all ones, but it is not possible because that will become non-normalized and we have to actually normalize it. So we put 4 by force a 0 there to make it normalized. And then we have smallest negative over here. So this is the largest negative number that we can save, means smallest magnitude negative number that we can save. So remember, these two values are roughly normalized. Then we have smallest negative. Smallest negative, for smallest negative, we have to have smallest negative Mantissa and largest positive exponent, because we want to move point as far as possible to make it further small. Now, this is our system. So these two values, remember, these are roughly normalized. We have to keep it in focus because if we don't consider it, that will make it non-normalized, and non-normalized numbers are not saved by the computer. So we can say to the mark that the smallest positive and largest negative numbers are not exact representations in floating point, and that makes it another reason not to have it for financial values or wherever we want to keep rounding off at bay. Now, let's start solving it. State floating point ranges in 5 bits Mantissa and 3 bits exponent. Now, 5 bits Mantissa and 3 bits exponent. You have to keep this chart in mind. If we have got more bits in Mantissa, what actually happens that we increase this rightmost bit towards the right. And if we have got less bits in Mantissa, we start removing these bits. So let's say if we have got 2 bits, we will remove these 2 bits. If we have got 7 bits, then these are 4, and then we will increase 1, 1, 1, 1, another 3 times to make it 7. Same happens over here in exponent. The rightmost bit is increased or decreased. So whatever the rightmost, if it is largest positive in exponent, then 1. Otherwise, if it is smallest negative, then 0, then 0, then 1. So if it is 5 bits, we take it 1, 2, 3, 4, and another 1, 5, and 3 bits exponent, then we will remove this. So this would become 0, 1, 1. Now let's start solving it. It is 3. So 0.1111 into 2 to power 3, and we move the point towards the right 3 times. This will become 7.5. So in 5 bits mantissa and 3 bits exponent plus 7.5 is the largest number, largest positive number that we can save. All right. Then we have got next smallest positive number. Smallest positive number is 0, 1, 0, 0, 1, 0, 0. So 0, 1, 0, 0, 4, and we will increase another 0 to make it 5 bits, and then we will remove this 1 to make it 3 bits exponent. Now, this will make it 0.1 into 2 to power minus 4. So this is 1, 2, minus 4, negative exponent. So we will move the point 4 positions towards the left. 1, 2, 3, 4. So we will fill zeros in it. That will become 0.00001. This is now 0.5, 0.125, 0.5, 0.25, 0.125, 0.0625, 0.03125. That is the number. You may show it this way or this way or this way. It's up to you how you like to, but this is 0.03125, which is the smallest positive number. So remember, if we like to save 0 in 5 bits mantissa and 3 bits exponent, actually we will be saving 0.03125 as 0, not 0 as 0. Then we have got negative, largest negative. Remember, largest negative is the smallest magnitude negative number. That number is actually, we will take from here 5 bits, 1, 2, 3, 4, and another 1, 5 over here, and 3 we will be removing this 0 and 1, 0, 0. So let's solve it. Since it is a negative number, first let's convert it to the positive side. We keep the exponent same to the first one. We will keep the mantissa same and toggle the rest. This is how we have got the positive form of it. And then we will put point and make it standardized, and then afterward we solve it. So point will go all the way towards the left. Since calculators will not be allowed, we may put it this way. So this is a positive point, 2 to power minus 5 plus 2 to power minus 8. It is positive, so we put brackets and we put negative sign to show it that it is the largest negative number that is possible in 5 bits mantissa and 3 bits exponent. Afterwards, we have got a smallest negative. Smallest negative is farthest from the 0 on the negative side, means that it has got the highest magnitude possible. So this is -1 into 2 to power whatever. All right. So 3 bits mantissa, 1, 0, 0, 0, 0, and 0, 1, 1. So this is 1.0 into 2 to power 3. So we know that this leftmost bit is a negative sign. We cannot do anything else, but we know that whatever the number is, it is actually negative, because negative sign in mantissa is 1, which is actually making it negative. So this is actually negative into 2 to power 3, which makes it 2 to power 3 negative minus 8. So this is minus 8. That is the smallest negative number that we can save. So now we can see that the largest positive number that we can save in 3 bits mantissa, 5 bits mantissa and 3 bits exponent is plus 7.5. The smallest negative is 0. The smallest positive is 0.03125. Largest negative is minus 2 to power minus 5 plus 2 to power minus 8. And the smallest negative number which is the largest magnitude negative number, that is -8. Now, sometimes we have got questions for 8-bit mantissa and 8-bit exponent. Larger the number, it becomes tougher for us to sort out the issue without calculator. So we go with few assumptions. Now, if it is the largest positive numbers in 8-bit mantissa and 8-bit exponent, then in that case we have, you can see that all ones filled for the zeros, for the bits available. So 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. So this would make it 0.11111 into 2 to power 127. In that case, what happens that we assume that these are so many ones after the point in mantissa that almost they are one. So we just take it as one. We approximate this number of ones as positive one. So this would become +1 into 2 to power 127. So this is plus 2 to power 127. Remember, these assumptions are there and you have to live with it. And then we have got smallest positive. Smallest positive is 0.1 into, remember, as per this chart, we are going as per this chart. So if we have got 8 bits, so we will be increasing this 0 8 times, and we will be increasing this 0 8 times. Now, smallest positive 0.1 and all zeros and this. So this would become 0.1 into 2 to power minus 128. We move point another point towards the right and we make it 0, 2 to power minus 129. So this is our answer. Is 2 to power minus 129 means we move the point to the farthest side 129 times, then it would become 0.129 zeros and then 1. This is the smallest positive number that we have. And largest negative number means the negative number that is closest to 0 on negative side. So this would be, when once we convert it from negative to positive, this becomes 0.10000001 into 2 to power minus 128, and that is how we get the answer over here. The smallest negative number farthest from the 0, that is minus 127. So this is it for ranges. Ranges are an integral part, and remember that we have got these questions in past papers where we have to have these ranges worked. I'll be uploading these slides in the definition under this video, and let's discuss few of the problem that may arise if we use floating point numbers. These are called, as we know, that because of the problem in the size of mantissa, we may have problems. So let's discuss a website as well as one of the computer program to identify these problems and how to answer those. So hold on. This is a good website to understand these issues. This is called rounding errors in floating point. The website address is floating point guide, floating-point-gui.de, floating point guide. And it actually is showing these errors. So what are these errors? Basically what happens, let's say if we have got two numbers, 0.1 and point 2, point 1 and point 2, and if we add them, instead of having point 3, what do we have over here? We have got 0.300000004. So why do we have these numbers? So what basically happens that neither point 1 nor point 2 can be represented in computer's floating point, as we know that point 1 and point 2 are not possible. 0.25 is possible, 0.5 is possible, 0.75 is possible, and the whole one is possible. Between 0.8, 0.7, 0.6, 0.4, 0.3, 0.2, 0.1 are not possible, because these are the denominations best possible to be seen with the denary numbers basis, but not binary numbers basis, because on the fractional side, when the number decreases, it decreases by half. In our number system, when the number decreases on the right, it decreases by tenth of its value. So 0.1 and 0.2. So what basically happens that when computer saved 0.1, it saved with a number which is closest to 0.1. And similarly, if a number is saved, 0.2, uh, 0.2 number is saved, so it is also saved with. So there were two errors right in the beginning. Neither 0.1 nor 0.2 were saved without errors. So there were two errors. So when we add these two errors together, there is another error in this question. Answer is errorful as well. So what does it mean? It means that computer tries to make it up to the point the error does not get accumulated and becomes significant. So these are called rounding errors. There are other errors as well. You may go this website and observe it yourself. So, but over here we are only comparing, studying rounding errors here only. So there are rounding errors, and this website explain it properly. Let me show you this error with the help of Visual Basic. How does it become, and how can we get rid of these errors? Let's start a project, console based. So let's have two variables, and as we know that there is a data type called single. So let's make it a as single variable. Single means the word size is 4, out of which 3 bytes are available for mantissa and 1 byte for exponent. And then we have got b as integer. So for b is equal to 1 to, let's say, 20. Let's say I have made a as 0.0, and I'm adding a is equal to a plus 0.1, and console dot write line a, and console dot read key. Now what is actually happening here, pay attention to it, that we have got a variable which is single. Single means it is in floating point form. In Python it is float data type, and it has got 3 bytes in mantissa and 1 byte in exponent. Total word size is 4, and we initialize it with 0.11. Then we run a loop, for next loop for 20 times, and in every loop we are adding 0.1 to a. We know that 0.1, 0.2, 0.3, 0.4 cannot be saved. Similarly, 0.6, 0.7, 0.8 cannot be saved. So we want to see that how the error is accumulates and when does computer show it. Remember, modern programming languages try to make up with this issue as much as they can, but once the error is accumulated to the point that it cannot be dealt with, then it is shown on the screen. Let's see. So we can see over here, computer actually tried to hold it as much as it can, but after zero point 0.7, the error becomes so much significant. It got accumulated in computer that computer has shown it. So instead of zero point 0.8, it has shown 800000001, and then 0.9, and then once the error is accumulated and it is shown, it is got rid of, and then computer started off with the further numbers. Now, how do we remove it? By having more bits in Mantissa. We know that why these errors are being accumulated, because we don't have first exact conversion of 0.1, 0.2, 0.3, and secondly, because of these flaws, errors are being accumulated, rounding off is happening. So now instead of single, let's take it double. Double means that now we have got a word size of 8. 7 bytes are in Mantissa and 1 byte is in exponent. As we know that we need more accuracy in Mantissa, and systems do not pay attention to uh, exponent. Exponent size remains same from single to double, because exponent is having as much as -128 to move points towards the left, and plus 127 to move the point towards the right if it is 1 byte exponent. If it is Mantissa, then having more bytes in Mantissa means that we have got more accuracy, which is required more than having such large numbers. So let's, in this case, you can see the error is removed. Obviously this error would appear, but if I go for like 50 times or 100 times, then that this error would show up. Obviously that would go beyond the strength of even a double float, but for smaller numbers which were occurring when the size was small are now gone. So this was it, and let's now see how, if we are actually having a number that we cannot show in exam. Let's say if they ask you to, what if they ask you to solve a question whose direct conversion is not possible for the fractional part, for example, 0.8. There are two methods. One is your assumption. So if it is 0.8, go with 0.75. It is 0.6, go with 0.5. The other one is that, let's say if you have got, hold on, let me show you. Okay. So let's say you have got a number which is 10.3. So either you may go for 10.25, or there is another way, that is 0.3, and you multiply it by 2. This will make it 0.3 multiplied by 2. This will make it what? 0.6. 0.6. So we have got a 0 over here, this one. And then we will multiply 0.6 by 2. This will make it 1.2. So this time we will take this one and put it over here. And then we will go further, 1.2 multiplied by 2. This will make it 2.2. So how, let's say if we have got less bits with it. So this is actually the case. So we keep multiplying, and whatever the point part we have got, we keep it, and then don't go with 1.2, rather with zero point 0.2. 0.2 into 4, that is 0 0.8. 0 point, and take 0 over here now. So let's say if we have got 7.4. So what we do, we will first pay attention to this 0.4. This 0.4 into 2. So this would become 7, sorry, 7.4. So how do we do it? First thing is that we take 0.4, multiply it by 0. Multiply by it, multiply it by 2. This would become 0 0.8. So we take this 0 and put it over here, and then 0 0.8 multiplied by 2. This will make it 1.6. We take this 1 and put it over here, and then again we take 0.6 and multiply it by 2. This will make it 1.2, and then we take another 1 over here. Let's say we have got 4 bits in exponent, and then we take 0 0.2 and multiply it by 2. This will make it 0 0.4. Then we take this 0 and put it over here. So you see, this got convert to 111.0110. So 0.110 becomes what? 0.5, 0.25, 0.125. So this is 0.25, 0.125. What it makes? So instead of 4, we will be having 7.375 as the closest number that we can use to store zero point 0.4 in floating point. So let me revise. If we have got a number that cannot be directly converted to the form which is closest, which is exact in floating point, for that first we have to consider that which number instead of zero point 0.4 we should take in fixed point. So what we do, we will start multiplying this point part, decimal part, by 2. So 0 0.4 multiplied by 2 becomes 0 0.8. So we take this 0 and put it over here, and then we take zero point 0.8 and multiply it by 2. This will become 1.6. So we'll take this 1 and put it over here, and then afterwards we just take zero point 0.6 and multiply it by 2. This would make it 1.2, and we will take this 1 and put it over here. Then we will take zero point 0.2 and multiplied by 2. This will make it 0 0.4. So we put this 0 over here. So this way we have to go as many times as the number of bits in the decimal side. Once that is done, we solve it and we get the number that is closest to the number that we have actually in fixed form. And now we will take this number and convert it to its uh, floating point form. So this is it for floating point numbers. Try solving few questions from the past papers, and these past papers are available online. Meanwhile, if you have got any questions to ask me those questions. There are assignments and past paper topical questions available on the website. If you like to visit that, let me show it to you. This is our website, ZAK-Bandashah-MYM. Go to A2 level over here. A2 level, and we have got this 3.1.3, 3.1.3 notes, assignments, video lectures, past paper topicals, past topical solutions, assignment solutions, past topicals. If you go with past topicals, you will see that we have got few past topicals over here. And if you will go with the assignments for 3.1.3, there are 3 assignments over there. Try solving these assignments. Remember, this is 3.1.3 in paper 3. So that's about it for the lecture today. Next lecture will be for arrays, and stay tuned. If you like these lectures, please share so that other could also be benefit with it. So thank you very much. Take care.